Welcome, ladies and gentlemen. This is going to be the video on the first of our secondary topics in equilibrium. This is going to be the one where we discuss and introduce common ions. We have three secondary topics of equilibrium: common ions, buffers, and titrations. And they are presented in this order for a very big reason. They really do follow one after the other, meaning we're going to be using what we learn about common ions to learn about buffers, and we're going to be using what we learn about buffers to actually learn about titrations with weak acids or weak bases. But this is the common ions video. So what I really want to stress with all of these secondary topics is we are absolutely still using the entirety of our skill set from the primary topics. You're still going to be writing equilibrium expressions. You will still be possibly determining K from concentration, and you will possibly be determining concentration from K. So we need all of those primary skill sets in order to address these topics. So first up, the common ion effect. The huge thing that you have to realize with common ion problems is that if you are dealing with an ionic compound that is in solution, it dissociates completely. And if you have a compound such as a weak acid, a weak base, or an insoluble salt, basically a Ka, Kb, or Ksp type of problem, and in addition to that compound, you have a second compound in solution that shares an ion in common with your weak acid, weak base, or insoluble salt, then we get what's called the common ion effect. What is the common ion effect? The common ion effect is basically this point right here about percent ionization. If you have a compound, like I said, a weak acid, a weak base, or an insoluble salt, Ka, Kb, or Ksp type of compound, and you have something else in solution that shares an ion in common with your weak acid, weak base, or insoluble salt, so it's something else that contributes to something that might be in that K expression, it cuts your percent ionization of that original compound way down. Having something already there in solution that is part of the equilibrium expression for that compound significantly decreases the amount that that original compound is capable of dissociating. And in order to sort of realize if you have a common ion in solution, you must absolutely remember this point. Weak acids do not react with their conjugate base, or aka their common ion. That is their common ion, that thing that's already there, that ion that they share in common. Weak acids do not react with their conjugate bases. They don't. They're two sides of the same coin. They do not react with one another. HF versus F minus. HF does not react with F minus because they're a conjugate acid-base pair. Similarly for Ksp problems, if you have one of the ions in solution that came from your insoluble salt, it will not react with the soluble salt. It's simply something that's already there. Basically, if you have something in solution that's a part of your equilibrium expression, the Ka, Kb, or Ksp, for that particular compound, it does not actually react with it. It's simply a part of that equilibrium expression. And essentially what this is doing, this is realistically, this is a Le Chatelier shift, and I know we haven't really spoken about Le Chatelier yet, but this is essentially like starting with a large amount of product rather than a large amount of reactant. And if you start with a large amount of product, you know that Le Chatelier says, what direction are you going to go? You're going to take that product and turn it into reactant rather than have the reactant generate some product. So meaning we're sort of cutting back on the ability of our original compound to dissociate by having something already there in solution that was already dissociated. These are the types of problems that I have been sort of alluding to with the primary topics, where I said if there's absolutely no information about the problem about starting with any of your products, then your products start at zero. Well, common ion problems, here's where that changes. We are now no longer going to be starting with zero for our products necessarily. We might have a certain amount of our products already at hand. That's what the common ion effect is essentially saying. And if you do have a certain amount of your products already there, that severely diminishes the percent ionization of your reactant. Now, the absolutely crucial key to doing common ion problems is realizing this last point right here. The reactions that you're writing are identical to the reactions that you've been writing thus far. You are writing Ka, Kb, Ksp reactions. You are not writing like HF plus F minus. That does not happen. Weak acids do not react with their conjugate base. You would write HF goes to H plus F minus. But instead of starting at 0 for your F minus, now you might be starting at a certain initial value. Also, a critical point to realize is that soluble ionic compounds dissociate completely, meaning you have to interpret the ionic compound that's been given to you and think about what ions it will become when you put it into solution. So really, this is best illustrated with practice problems, and I'm going to go through 3 here. 2 of them are Ka, and 1 of them is a Ksp, and we're going to see how this common-ion effect affects the type of equilibrium stuff that we're doing. So calculate the pH of a solution containing 0.085 molar nitrous acid and 0.10 molar potassium nitrite. Now, the 3 steps to solving any equilibrium problem, and this completely applies to common ion problems as well, are number 1, write a reaction, number 2, fill out an ice chart, number 3, plug the stuff from your ice chart into your expression and solve. Solve for whatever it is that you're looking for. So we do want to start, and I am going to start here by writing the reaction. Now, the big question is, what reaction do you write? Remember, the problem gives you enormous clues as to what reaction you're meant to write here. In that, they gave you a Ka. So you want to write a Ka reaction that goes with this Ka value. Now we're dealing with nitrous acid, so remember, X become ites become us. So this is based on the nitrite ion, which is 1 less oxygen than nitrate. Nitrate is NO3 minus, so nitrite is NO2 minus, and this is nitrous acid, so this is HNO2. So we want to write HNO2 dissociates into H plus NO2 minus. So that's just straight off the bat, even without looking at my numbers, I know I should be writing this reaction because I've gotten, you know, a Ka value for nitrous acid. All right, well now I want to start thinking about what it is that's in this beaker. So I'm going to draw a little picture here, which I'll eventually erase. So in this beaker, it says we've got the solution, and the solution contains 0.085 molar nitrous acid. Well, that's HNO2, right? So we have that floating around in solution. And, you know, a little bit of it dissociates into H plus and NO2 minus, but you know that's really what we have in solution. For the most part, it's HNO2. And then 0.10 molar potassium nitrite. Okay, so we have to think, what is the formula for potassium nitrite? Well, potassium is K with a charge of +1. Nitrite, which we already had to think about for nitrous acid, is NO2 minus. So potassium nitrite is KNO2. But before I put that into my beaker, you have to think about ionic compounds. You put this thing in water. This is soluble. I know it's soluble because it's a group 1 ion. So I put this thing in water, and it will immediately dissociate into K plus and NO2 minus. It's not KNO2. And that is an enormous point about these common ion problems. This is not, potassium nitrite in solution is not KNO2. It is potassium, and it is nitrite. And you need to start seeing these compounds this way as not being some sort of whole that cannot be broken apart, but instead as the 2 parts that went into making the whole. You see potassium nitrite, you need to really zero in on the, okay, this is K, and it's NO2 minus. So that means that for the potassium nitrite in solution, what do we have? So I'm going back to my beaker. That means that we're going to have some K plus, and we're going to have some NO2 minus floating around. A few things about this beaker with this potassium and this nitrite and this nitrous acid. Thinking about whether or not the salt is acidic, basic, or neutral. We know it's all about thinking about the conjugate acids and bases. So like if I take this K plus and think about what base it came from, that's KOH, and I think about this NO2 minus and I think about the acid it came from, oh, hey, look at that, it came from HNO2. Now KOH, that's a strong base, which means that this K plus is neutral, which means that it will not react when it is in solution with things that are acids and bases? It will not. That potassium there, that is simply a delivery mechanism. That potassium is doing absolutely bupkis in your solution. It's just literally floating around and watching other things react. It is truly a spectator ion. It does absolutely nothing. But the nitrite from the potassium nitrite is also in solution, and it is the common ion. So in terms of doing the equilibrium problem, that means that we've got this nitrous acid, in a solution that already contains some of its conjugate base. So if we go to the ice chart, this changes how we fill it out a little bit. So it says that we've got 0.085 molar nitrous acid. We know that that's the initial concentration of the nitrous acid, because whenever it's given to you, that's always, for a weak acid, it's always going to be the initial concentration. Then, there's absolutely nothing in the problem that says we're starting with a certain amount of hydrogen ion. There is no mention of the hydrogen ion, so that means that we're starting at 0. However, 0.1 molar potassium nitrite dissociates completely into 0.1 molar potassium, which who cares about that because that does nothing in solution, and 0.1 molar nitrite ion because they're in a 1-to-1. KNO2 makes K plus and NO2 minus. Everything's 1-to-1. We are not starting at 0 for the nitrite. We already have nitrite in solution. So these are those problems that I mentioned where the problem tells you, like, hey, we're not starting at 0 for all of our products anymore. Now, the nice thing about the common ion problems is that this right here, what I've done so far, is the only thing that changes in the common ion problem. The rest of the problem is going to be exactly the same to the other types of equilibrium problems you've done thus far, meaning you want to fill out the ice chart as best as you can and then go to the K expression. And in terms of filling it out, really, from now on, it's no different, meaning we don't have any equilibrium concentration, so our changes are going to be X. And it's going to be minus X plus X and plus X, because everything's 1-to-1-to-1, so you want to make your reactants go down, your products go up, and this is going to be 0.085 minus X, which I will say is approximately 0.085, because my K value is on the order of 10 to the minus 4th. The H plus concentration is just X, and now here, 0.1 plus X, again, I can say that that is approximately 0.1 molar, because the reason I don't want to have the molarity plus X or minus X, because that would invoke then the quadratic equation to the quadratic formula to solve for that, and I don't want to do that. So I am going to be making this assumption twice. So I've got my ice chart filled in. Really, like I said, the big difference was knowing that we're starting not with 0 for everything, but, you know, potassium nitrite gives me 0.1 molar nitrite, which means that I'm starting with a certain amount of my product. So I'm going to write the K expression because that's the next thing that we do. Hydrogen times nitrite divided by nitrous acid. And then plug in, so the K value, 4.5 times 10 to the minus 4th, is equal to X, now times 0.1, right, because I've got initial concentration of the nitrite, divided by 0.085. And then the rest of this is just solving as usual. So I'm going to erase my ice chart. When you solve this, you get an X value of 3.825 times 10 to the minus 4th molar. And when you look at your ice chart, what you wrote, X here represents your equilibrium concentration of the hydrogen ion. That's what X is standing in for. So we want to take the negative log of this value to get pH. When we do that, we get a pH value of 3.42, and you do want to do your check because you made an assumption, so you want to check it. Now, in this case we made 2 assumptions. You do not have to check both assumptions. You only need to check one. And the one that you want to check is the one that where you assumed with the smaller value, the smaller number. Because if it's less than 5% ionization with the smaller number, then you know for sure it'll be less than 5% ionization with the larger number. So the smaller number that we compared X with was the 0.085. So I'm going to take my 3.825 times 10 to the minus 4th, divided by that 0.085, multiply that by 100. If it turns out to be less than 5%, we're good. And it does. It turns out to be 0.45%. So that's our check, and everything is cool. So that's the common ion problem. Basically, the common ion problem is starting with a certain amount of product already in solution. So we're going to do one more Ka problem, because I want to show you how it can be really, really tricky and really mean in a Ka problem. So this one right here, calculate the pH of a solution that is 0.06 molar in acetic acid and 0.04 molar in calcium acetate. Ka for acetic acid is given to you 1.8 times 10 to the minus 5th. So we start by writing our reaction. What reaction do we write? They give us the Ka value for acetic acid, so we want to write the Ka reaction that goes with it, meaning the acid dissociation reaction for acetic acid. So acetic acid, HC₂H₃O₂ goes to H plus the acetate ion. And, oh, nope, C₂H₃O₂ with a charge of -1. And then we're going to fill out the ice chart. So what do we have in our beaker? We have in our beaker, we've got acetic acid, that's 0.06 molar. That's great. And then we also have in our beaker calcium acetate. And hopefully you're thinking that this is not calcium acetate, this is calcium and it's acetate, because absolutely that's what calcium acetate is. You put it in solution, it's ionic, it's soluble, so it will dissociate completely. You no longer have calcium acetate, you have calcium ions and you have acetate ions. The calcium ion does nothing, it's not a common ion for this equilibrium problem, but the acetate ion is. So we're not starting with any hydrogen ion, but we are starting with some acetate. And if you plug in 0.04 molar as that initial concentration of acetate, congratulations, you just got the problem wrong. Be very mindful whenever Mrs. Julian gives you a name of something without giving you the formula, because calcium is group 1, acetate has a charge, calcium is group 2, calcium has a charge of -1. This is the formula for calcium acetate. It is completely soluble. Therefore, when it dissociates like this. So if I have 0.04 molar calcium acetate, it will generate 0.04 molar calcium. Who cares about that? But because of the 1-to-2 relationship between the calcium and the calcium acetate and the acetate ion, I am actually starting with 0.08 molar of the acetate. I am sure we're all doing our test corrections for the acid-base test, and you might have fallen prey to that particular question. I know I threw one of those on there. So our initial concentration of the acetate is not 0.4, and it's certainly not 0. It's going to be 0.8. But from this point on, the equilibrium problem is exactly the same as all our other equilibrium problems. We're starting with a certain amount of acetate already in solution. It does not react with the acetic acid. Weak acids do not react with their conjugate bases. Insoluble salts do not react with any of the ions that they are made up in. They're flips of the same coin. It's simply already in the pool. So filling out our ice chart, minus x plus x plus x, because everything is 1 to 1 to 1. So equilibrium 0.06 minus x, which is approximately 0.06, x, and 0.08 plus x, which is approximately 0.08. Go to the equilibrium expression. By the way, an abbreviation for acetate and acetic acid is this OAC minus. I'm using it on shorthand. Feel free to use it on anything that is not officially graded. Do not use it on the AP exam, please, but it is shorthand because chemists are lazy and we use acetate a lot. So then we're just simply going to plug everything in. So this is 1.8 times 10 to the minus 5th is equal to x times 0.08 divided by 0.06. Then you solve So this is truly, truly identical to the other types of problems we've been doing thus far. We're solving for x here, so we get a value of, checking my notes, 1.35 times 10 to the minus fifth. And that is equal to our hydrogen ion concentration, so we want to take the negative log of that, right? Negative log of 1.35 times 10 to the minus fifth. We get a pH of 4.87, right? And then our quick check, we want to compare this to the smaller number. So 1.35 times 10 to the minus fifth compared to 0.06. Multiply it times 100. If this number is less than 5%, then we're good, and we actually get 0.0225%. So it's significantly cutting down on these percent ionizations from like 1% or 2% to now, you know, 100th of a percent. And then doing one with KSP. Very, very similar. This is all very, very similar. Calculate the molar solubility. Now remember, in KSP problems, this might be how they ask you for something. The molar solubility, moles per liter of silver chromate at 25 degrees Celsius in a solution that is 0.075 molar in calcium chromate. KSP value of silver chromate is 1.1 times 10 to the minus 12th. So we want to start by writing a reaction. Once again, what reaction are we writing? They gave you a massive tip-off. They gave you the KSP value for silver chromate. So you want to write the silver chromate dissociation reaction. Ag₂CrO4 solid goes to 2 silver ions, because of the subscript for the silver, plus the chromate ion. And these guys are aqueous. And once again, sort of thinking about what's in the beaker, we're putting silver chromate in the beaker. Most of it will stay as a solid, but some of it will dissolve into silver and chromate ions. We're all in that beaker already. There is 0.07 molar calcium chromate. Now we are assuming that that one is soluble because they're telling us, basically they're telling us so, 0.075 molar. We can assume that this thing completely dissociates. So if I have calcium chromate and it completely dissociates, and I have 0.075 molar of the calcium chromate to begin with, if it's in a 1-to-1, that means that I get 0.075 molar of calcium and 0.075 molar of chromate. Again, don't see this as calcium chromate, see it as calcium and chromate. Know how to split it, feel comfortable with charges. Who cares about the calcium? Calcium is not in the equilibrium reaction, which is for the silver chromate that we wrote up here, but chromate is. So we're trying to dissolve this silver chromate in a solution that already contains some chromate ions. So instead of starting at 0, we're starting, for our products, we have an initial amount of them. You also need to remember that if it's asking for the molarity of the silver chromate, you're going to get there via coefficients. You're going to use coefficients to turn the molarity of one of the products into one of the reactants. That's a facet of most KSP problems. So you do need to calculate the molarity of the products and then use that to figure out the molarity of the reactants. So we're going to set up an ice chart. I'm going to cross off the silver chromate because it's a solid, so it's not going into the equilibrium expression. We're not starting with any silver in solution, but we are starting with some chromate in solution. Now for changes, the silver will be plus 2x. Why is it 2 and not 1? Right there, because of your coefficient. Don't lose that. Remember that your changes are based on stoichiometry. The chromate change will be plus x. So equilibrium concentrations for the silver is 2x, for the chromate is 0.075 plus x, which I will assume is approximately 0.075. Why? My K value is significantly less than 10 to the minus 4th. It's on the order of 10 to the minus 12th, which tells me that my percent dissociation is going to be very, 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 very small, and x compared with 0.75 is probably negligible. So I'm going to go to my KSP expression. Silver ion concentration squared, because of the 2, that has to stay there, times the chromate concentration, raised to the first, and then we're simply going to plug in, right? Nothing on the bottom because it's KSP, we don't include solids. So 1.1 times 10 to the minus 12th is equal to, plugging in, 2x. Now you have to actually square that, right? 2x as a unit squared is not 2x squared. It's actually 4x squared times 0.075. Then it's just math, right? From this point forward, this is just math. So 2x is a unit squared, which becomes 4x squared, and then times 0.075. Know your algebra and feel comfortable solving this. When I solve this, I get that x is 1.9 times 10 to the minus 6th. Now, when you look at your ice chart in terms of what x represents half of the silver ion concentration, right? Because 2x is the silver ion concentration, and x is half of that. But we actually like x. Having x here is good because of coefficients, because of stoichiometry. X is actually equal to the molarity of the thing that we want, the silver chromate, right? Because if the silver is 2, and then the silver chromate is 1. So if x is 1.9 times 10 to the minus 6th, then if x is 1.9 times 10 to the minus 6, 2x is 2 Ag, then Ag2CrO4, right? That's actually what we want. So this right here is actually the answer to the question, 1.9 times 10 to the minus 6. We do need to do the check, though, compared to the thing that we assumed with. So check 1.9 times 10 to the minus 6 divided by 0.075 times 100. If this turns out to be less than 5%, we're good. And my smartboard just froze for a moment. But hopefully you can see that, yeah, that's going to be significantly under 5%, like 0.0025. So it's way under, which means that we're good. So with common ion problems, the key, as always, is sort of interpreting the question, writing the correct reaction. You're writing the exact same problem reactions that you were writing before, but now instead of starting with 0 for your products, you've got to interpret the problem and figure out that, oh, okay, you know, I'm not starting at 0 in this case for the chromate. I actually have some chromate that's already in solution. It doesn't react with the silver chromate, but it makes it harder for it to dissociate.